All right, for our second lecture of the week, I wanted to do a quick review of what we were working on last time because it leads directly into the new material. We were looking at the work done by a spring force. We know that for most springs, you can use Hooke's law, the equation that says that the force of extending or compressing a spring is equal to negative kx, that k being the spring constant, which just relates the amount of force exerted on a certain spring to the distance by which it extends or compresses, times x, which is the distance that it extends or compresses. A spring with a large value for k would be considered a very stiff spring, like, for instance, the spring in the suspension of a car, versus a spring that has a very small value for k, which would be considered a very weak spring, or not a very springy spring, and that would be something like maybe the spring in a ballpoint pen, or that kind of thing. Force, though, is useful to know, but very often we would rather know how much work is done by a spring or on a spring in order to extend or compress it by a certain amount. And so the equation for the work done on a spring, if the spring goes from position A to position B in the x direction, and we normally define the x direction as the direction along the axis by which the spring is being stretched or compressed. The work is the integral of the force in that direction. And we arrive through various calculations through to the work of this on the spring being equal to negative 1/2 the kinetic, sorry, not kinetic energy, negative 1/2 the spring constant times the x squared value for position B minus the x value for the position at point A squared. So it's basically the change in position squared. And that makes a big difference versus force, which is just k times the position to the first power. Okay, the work done by the spring is also independent of the path between point A and point B. And this brings us to the next example in the text, which is about the work done on a spring. In this example, we have a perfectly elastic spring. When we say perfectly elastic spring, we just mean that it obeys Hooke's law, that it has that a spring constant really is constant. That describes most springs, although I think I've mentioned before that there are some springs for specialized uses where the k value, or the spring constant, can actually change depending on how much of a load is placed on the spring. But we don't really encounter those here because those are highly specialized and very unusual. So we have a perfectly elastic spring that requires 0.54 joules of work to stretch it 6 centimeters from its equilibrium position. The equilibrium position of a spring, again, is just the position that it's normally in when no outside forces are acting on it other than its own weight and the normal force if it's sitting on a surface. But no stretching or compression forces are acting on the spring when it's at its equilibrium position. The equilibrium position is usually considered to be 0, although you could assign another value for it if you wanted to, but that would just make things more complicated. So we usually call it 0. And so the question is, what is the spring constant k? Well, we have an equation up here that involves work and how much the spring is stretched, and k. The problem is that that equation is not solved for k. So what we can do is solve that equation for k. And we can do that step by step. I didn't have it step by step in this example here, but if work is 1/2 k times xb squared minus xa squared, and what we want is k, then basically we have to get k alone on the right-hand side of the equation. And to do that, we can just basically divide both sides by everything that's multiplied by K. So we can divide both sides by 1/2. Dividing by 1/2 is the same as multiplying by 2. So I'll just put a 2 in front of the W, and that gets rid of the 1/2 on this side. And we could divide by this whole part of the equation here, x squared b minus x squared a. And that gets rid of this part of the equation. And we've solved for K. So it turns out that K is 2 times the work over x squared for position B minus x squared for position A. And I've outlined it because this is a general equation that applies to any situation, not just this situation. So you could use this equation for essentially any spring in any situation. Okay, we can start putting in the numbers. The 2 is a 2, of course. Work is 0.54 joules. XB is 0.06, but that needs to be squared. 0.06 meters, because notice it said 6 centimeters, but distances need to be in SI units, and that would be meters. So 6 centimeters would be 0.06 meters. And that's minus the A position, which in this case was the equilibrium position, which is 0 meters squared. Okay, so that's 1.08 over 0.0036 square meters. And if you look at the units, a joule is a kilogram meter squared per second squared. So 1.8 kilograms meter squared per second squared over 0.0036 meters squared means that the meters squared cancel, and you get 300 kilograms per second squared. And that may not seem like a very sensible unit, but actually that is equivalent to newtons per meter. So 300 kilograms per second squared is the same as 300 newtons per meter. And that's because 1 newton per meter is 1 kilogram per second squared. And newtons per meter would be the SI unit for the spring constant. Okay, because it's the amount of force that it takes to stretch the spring a certain distance. So the SI unit for force is newtons, the SI unit for distance is meters, newtons per meter. Okay, the next question would be, how much work is required to stretch it an additional 6 centimeters? And you might think, oh, it's the same. But it would be the same if we were talking about force. The amount of force necessary to stretch the spring from 0 centimeters to 6 centimeters should be the same as the force needed to stretch it from 6 to 12 centimeters. But that's not true of work. So we need to use the equation for work. Work is 1/2 the spring constant, which we now know from here, times the x coordinate of point B squared minus the x coordinate of point A squared. So it's 1/2 times 300 newtons per meter times 12 centimeters, which is 0.12 meters squared, minus the original position, which for part B was 0.06 meters squared. And we work that out and we end up with 1.62 Newton meters. And remember, a Newton meter is a joule. So that's 1.62 joules. All right. Yeah, notice in the introduction, it said here that it told us how much work it required to stretch the spring from 0 to 6 centimeters. That was 0.54 joules. In order to stretch it from 6 to 12, it takes 1.62 joules, quite a bit more. So the amount of work it takes to stretch the spring increases as you stretch the spring further and further and further. And if you take an actual spring and stretch it, you'll actually feel that it gets tighter and tighter as you try to pull it further and further. Okay, this brings us to the next topic, which is kinetic energy. Kinetic energy is also known as the energy of motion. there are various symbols that can be used for kinetic energy. I tend to use KE for kinetic energy, but the book likes to use K, and a lot of other books like to use E sub K for energy subkinetic. So you might see any of these. The main formula, the formula that we normally use for kinetic energy, is kinetic energy is equal to 1/2 mass times velocity squared, or 1/2 mv squared. Mass is in kilograms, velocity is in meters per second. So if you take kilograms times meters per second, the quantity squared, you get kilograms meters squared per second squared as the units. And what do you know? That's a joule, the unit of energy or work. So the units work out. These normal units for kinetic energy would be joules, as for any other kind of energy. This is the equation that we use typically for a single entity or a single particle that we're finding the kinetic energy for. But there are also occasions where we want to find the kinetic energy for a system of particles. And in that case, the total kinetic energy is just the total of the kinetic energy of all the particles. Or in other words, K is equal to the sum of 1/2 mv squared for all of the particles. So that's a fairly simple concept. You can also express kinetic energy in terms of momentum. Momentum is mass times velocity, and momentum is also the derivative of kinetic energy. V, okay. And if you take the derivative of kinetic energy, with V being the variable, you've got 1/2 mv squared. And the 1/2 and the m are constants. The m is a constant because it's not the variable that we're calling the variable. And so it's 1/2 m basically times dv squared. And when you take the derivative of a number, of a variable, I mean like v squared, then basically what you do is you multiply the quantity that's being taken, you're taking the derivative, multiply it by the exponent, and then reduce the exponent by 1. So the derivative of this is going to be 2 times 1/2 m times v to the 2 minus 1 power, or in other words, mv. So momentum is the derivative of kinetic energy. Or that's also the same thing as saying that kinetic energy is the integral of momentum. Which you can show like so. Integral of mv dv. And the mass for our purposes is a constant. So we can take it outside the integral. Well, when you take the integral of a variable, you raise its power by 1 and then divide by that number. Okay, so that's going to be m times v to the 1 plus 1 over 1 plus 1. Or in other words, mv2 to the second power, over 2. Or 1/2 mv squared. So, it works either way. So they are related to each other, and so there's no reason that we can't express the kinetic energy in terms of momentum. Momentum, again, is mass times velocity. And what that means is that solving for velocity, velocity is momentum divided by mass. So you can just insert that into the equation for kinetic energy. And you end up with, ultimately, kinetic energy is momentum squared over 2m. And I've outlined this equation because that one is also general. It applies to everything, not just any particular example that we're working on. So momentum squared over 2m, that's kinetic energy. Okay. You could also, if you wanted to find momentum in terms of kinetic energy, you could look at okay, let's leave it in that order. Suppose you want momentum from kinetic energy. Well, you could do it the other way around. You could, well, if you got the kinetic energy, you could, of course, always take the derivative of it and get momentum. Or you could work it out like this. If kinetic energy is p squared over 2m, then you want to solve for p. First, you have to get rid of the 2m. Multiply both sides by it. And that gives you p squared is equal to 2mk. And then take the square root of that and you get p. So p equals the square root of 2 times the mass times kinetic energy. Okay, so that's how you can solve it the other way around. Okay, this is for a single particle. Of course, if you want it for an entire collection of particles, then you just sum up the kinetic energies or the momentums of everything, of all the individual particles. All right, so looking at the kinetic energy of an object, for example, 7.6, the question is, what is the kinetic energy of an 80 kilogram athlete running at 10 meters per second? Fortunately, both of these quantities were given in the requisite SI units. If they weren't, you would have to do a unit conversion in order to get kilograms and meters per second. And the kinetic energy is 1/2 mv squared. That's 1/2 80 kilograms times 10 meters per second squared, and that's 4,000 joules. You might also, wonder, I'm going to actually divert us for a moment. To put it in more familiar terms, what would be the kinetic energy of, say, a 3,000-pound car traveling at 60 miles per hour? In joules. Uh-oh. So now we're going to have to do some unit conversions because we've got mass, well, weight in pounds and speed or velocity in miles per hour. So pounds to kilograms is pretty easy. There's 1 kilogram for every 2.2 pounds. And so 3,000 divided by 2.2 gives us 1363.636363, blah, 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 on to infinity, but I'm going to call it 1364 kilograms because 4 significant figures is more than enough. Okay, so putting a decimal point at the end of the 3,000 makes that 4 significant figures, but even putting a decimal point after the 60 only makes that 2. So 4 should be more than enough here. So there's your mass. The velocity is 60 miles per hour. We want meters per second. So let's see, there's 1.61 kilometers for every 1 mile. That should cancel miles and give us kilometers per hour. But we don't want kilometers per hour. We want kilometers, or we want meters per second. So now we need 1,000 meters for every 1 kilometer, because kilo means 1,000, right? So there are 1,000 meters per kilometer. And that will take out kilometers, and we have meters per hour. And there's 1 hour for every 3,600 seconds. And that should take out hours and leave us with meters per second. So let's see, 60 times 1.61 times 1,000 divided by 3,600 gives us 26.83 repeating, I'll call it 26.8 meters per second. All right, so now we have KE, or kinetic energy, or just K as the book calls it, is 1/2 mv squared. So that's 1/2 1364 kilograms times 26.8 meters per second squared. And 26.8 squared is this times 1364 divided by 2. And that gives us, oh boy, let's go to scientific notation. No. Okay. Second. There. Okay. Okay, so it's basically 490,000 joules. So 490,000 joules, you could report it as 490,000 joules, or 4.90 times 10 to the 5th joules, or 490,000 would be 490 kilojoules. So that's a lot of energy. Even though joules are small, that's a lot of joules. And because, a car traveling down the road at 60 miles an hour has a lot of energy. Not surprising. So that's something that's, maybe a little more relatable. Anyway, part B, for example, 7.6 gives this crater in Yucatan, which I'm not even going to try to pronounce, but I believe that's the crater created by the asteroid that is believed to have ultimately killed off the dinosaurs because it threw so much dust into the air that it blocked the sun, resulting in a decrease in temperatures, which killed off the vegetation, which killed off the small animals, which eventually killed off the big animals. Anyway, the asteroid was traveling at an estimated 22,000 meters per second, and it released something like 4.2 times 10 to the 23rd joules of kinetic energy on impact. And so the question is, what is its mass? And this is probably actually how they did estimate its mass. They were, basically given the devastation that it caused, the size of the crater, they were able to estimate how much energy it would take to create a crater that size, and about how fast the asteroid must have been traveling, and then they back calculate what the mass was. Well, if we have kinetic energy is 1/2 mv squared, you can solve that for mass pretty easily. Mass is 2 times kinetic energy over velocity squared. And we have velocity and kinetic energy in the correct units, meters per second and joules already. So it's just 2 times 4.2 times 10 to the 23rd joules over 22,000 meters per second squared. And that ends up being 1.74 times 10 to the 15th kilograms. And so that was a very, very large asteroid indeed. Okay. Also, we've got a question involving much smaller quantities, individual neutrons that move around inside nuclear reactors. They travel at about 2,200 meters per second, and they want us to find the kinetic energy of one of those neutrons. The mass of a neutron, which I don't think they gave in the problem, but if you look it up, it's 1.68 times 10 to the minus 27 kilograms, because neutrons are really, really little. The kinetic energy is going to be 1/2 mv squared. we have the mass and the velocity in the proper SI units. So it's just 1/2, 1.68 times 10 to the minus 27 kilograms times 2,200 meters per second, the quantity squared. And that gives us an energy of 4.07 times 10 to the minus 21 power joules. So we've seen quite a range of values for energies in this case. An 80 kilogram athlete running at 10 meters per second is 4,000 joules. The 30,000 pound car traveling at 60 miles an hour is 490,000 joules. Whereas a single neutron, even though it's moving really fast, 2,200 meters per second, it has such a small mass that it only has a kinetic energy of 4 times 10 to the minus 21 joules. So there's a huge range of kinetic energies out there for various objects, depending on how big they are and how fast they're moving, especially on how fast they're moving, because it's 1/2 mv squared. So velocity counts more than mass does towards the kinetic energy. Okay, I'm a little over the time I wanted to take for the first segment of the video, so I'm going to cut it off there, and we'll come back in a moment with the relativity of velocity.